We will continue with our discussion on forces on bodies. We will look at some problems, and today, in addition to looking at one or two simple problems, what I am going to do is I will also look at the case of uniform circular motion with a couple of examples, and we will explain the case of skidding of a car on a circular track and the role of friction there. So, we start with a problem. We start with a problem of multiple bodies connected by strings, and we will take a very simple example. We have a frictionless table on which we have a mass m1, a mass m2, a mass m3. These are connected by strings, and at mass m3 the string is being pulled by a force of T3. So, what we have been given is mass m1, which let us say is 10 kilograms, mass m2 20 kilograms, mass m3 30 kilograms, all connected together by strings. And here what is given to us is m3 is being pulled to the right by a force T3 is equal to 100 Newton. So, a 100 Newton force is applied to the block on the right, and so all of them are moving. It is a frictionless contact. We have to find the axis. So, what we have to find in this problem is find acceleration of the blocks and the force in the string connecting m1 and m2 and the string connecting m2 and m3. That means we have to find the force in this string and the force in this string, and at the same time we have to find the acceleration of the blocks. Now, if the strings are inextensible, that means the lengths are constant, and if the lengths are constant, then the distance moved by block 1, 2 and 3 are same, and what this gives us is acceleration of block 1 must be equal to acceleration of block 2 must be equal to acceleration of block 3, and this we can call is the kinematical constraint which we get on this multi-body problem. We have problem of 3 bodies. So, actually there should be 3 accelerations, but because they are connected by inextensible strings, their accelerations are equal. So, A1 is equal to A2 is equal to A3. So, this is what kinematics tells us. Now, you may think that this will be the case every time, not today, but in the next class we will see problems where we have bodies connected by strings and where the accelerations may not be equal. And today we will just consider a very simple example. So, here all the 3 accelerations are equal. So, now as we have seen, to solve any problem we will draw the free body diagram. So, let us start. Keep in mind this is our original system. This force we have called this as T3, this is body 1, this is body 2, this is body 3, and this is a string, this is also a string. So, let us start with drawing the free body diagram. I draw the free body diagram of body 3. On body 3 we have the force in the string on the right given by T3 to us, then there is the weight of the body, there is normal reaction from the ground on the body. At this contact there is no friction, so there is no horizontal force, we only have the normal reaction, and we have the force which this string applies, let us call this as T2, which is now not known. So, we have, this is the free body diagram of body 3, and if I write this, we look at this, then in the y direction normal reaction and weight balance each other. So, there is that is the equation, we do not get anything. On the x direction what we get is T3 minus T2, this is the net force in the x direction, this must be equal to M3 times A3. So, this is the equation which I get. I first draw the free body diagram, I write the equation. Now, let us draw the free body diagram of body 2. On body 2 what we have is, this is body 2, we have, in fact I should put this as M3G, we have the weight of the body 2 acting M2G, this let me put it as N3, there is a normal reaction N2. Now, on body 2 the string pulls the body 2, so the force on body 2 by the string is in the right direction, we call it as T2, and there is a force which is the first string is applying, we call this as T1. And from here when we write the equation of Newton's law, when we apply this in the x direction, what we will get is T2 minus T1 is equal to M2 A2. Then we go to body 1. For body 1, this is body 1, we have the string force being applied here T1, and then we have of course N1 and M1G which are not relevant, and this is the only force we have. So, then what we have is, we get our equation when we now in the x direction when we apply Newton's law, we get T1 is equal to M1 A1. So, therefore, when we write the three equations, we have T3 minus T2 is equal to M3 A3, T2 minus T1 is equal to M2 A2, and T1 is equal to M1 A1. So, these are the three equations for the three bodies which we get. Now, we use the kinematical constraint and we say, we have shown A1 is equal to A2 is equal to A3, let us call this as A. So, therefore, all these three are equal. So, what we can do is, let us add up all these equations. When we add up all these equations, we get T3, T2 will cancel out, T1 will cancel out, will be equal to M1 plus M2 plus M3 times A, and since all these masses are given, so therefore, we can get the value of acceleration. This will be equal to T3 divided by M1 plus M2 plus M3. So, from here we will be able to get the value of acceleration A. Once we get the acceleration A, we can go to this equation, the first equation, and so we go to the first equation, let us write this. So, this implies we get A. Then we go to equation number 1, T3 minus T2 is equal to M3 times A. So, from this equation we can get the value of T2. T2 will be equal to T3 minus M3 times A, and then we can go to the first equation, T1, we already know this is equal to M1 times A. So, therefore, we can solve the value of T1, T2 and A. These are the three unknowns. T3 was given to us, there was one unknown, acceleration. So, we can solve a problem like this. When we work out the numbers, what we get is numbers acceleration A will turn out to be 5 by 3 meters per second square for the given values of M1, M2 and M3, and T1 turns out to be equal to 10 times A, and T2 turns out to be equal to 30 times A, and T3 works out to be equal to 60 times A. So, this is what we see also is that the tension in each string on the right keeps on reducing, and this particular example is something like an engine pulling train compartments. and this gives you the forces in the links between the various compartments of the train. And what we will realize is, if masses m1, m2 and m3 are equal, then you will be able to show T3 will be equal to 3 times ma, T2 will be equal to 2 times ma, and T1 will be equal to m times a. So, this is how one can work out the force between compartments in a train. So, having seen this example, let us now revisit the case of a body in uniform circular motion. We have already seen example of this, but let us once again recap this. When a body is in circular motion, that means it is moving in a circular track like this. Uniform motion means the velocity v has a constant magnitude, which we can write it as v, and its circular motion, that means it is moving in a path which is circular, let the radius of the path be r. So, whenever we have a body which is moving like this, then what we realize is that there is a component of acceleration which points towards the center. So, for a body to move in a circular path, there will be a component of acceleration toward the center, and this radial component of acceleration, which we can call it, this is equal to v square upon r. So, even if the body is moving with a constant speed, but the fact that it is on a curved path or a circular path has a, it gives it a radial component of acceleration equal to v square upon r. And this acceleration has to be provided by some force on the body. Unless this force is there on the body, it will not be able to move in a circular path. So, let us take an example of what is called as a conical pendulum. A conical pendulum, suppose we have a string. So, we have a string, we have a body, we have a string, we connect it with a mass m, a ball of mass m, this is a string. This is what we call as a pendulum. Now, what we do is, let us, this was the initial position of the pendulum, let us take it at an angle theta, and then we let this pendulum move in a circular path. So, if this pendulum moves in its own plane, this is what we call as a simple pendulum. But in case of a conical pendulum, what we do is, let me explain this again. This is the pendulum, this thing. So, first we take this bob or the pendulum, we make it move at an angle theta, and then it follows a circular path at this height. So, for example, if this length of the string is L and it is at an angle theta, then the conical pendulum, so this will be L cos theta, this will be L sin theta, this moves in a circle of radius r is equal to L sin theta, and the height or the height of the pendulum from the plane of motion of the ball, this is equal to L cos theta. And so, this is what is referred to as a conical pendulum. So, let us see the motion of a or uniform circular motion of a conical pendulum. And let us try to analyze this dynamically. So, therefore, what we have, as we have shown in the figure, this is a pendulum, this is at an angle theta, and this is traversing a circular path. If I draw the free body diagram of the ball of the pendulum, so then I draw the ball, what I have is its weight acting downwards, and we have this force in the string which we call tension, or we represent it by T at the angle of the string, and this angle which it makes with the vertical is theta. So, these are the only two forces acting on the ball of the pendulum, that is the weight acting downwards and the string force T. Now, because the pendulum, as I have shown here, is in a circular motion, then we realize it has a radial acceleration component which is equal to v square upon r. And this component of acceleration in this case, as I said earlier, there has to be some force which has to provide this acceleration, otherwise the body will not be able to move in a circular path, and in this case this acceleration is provided by the horizontal component of T. So, if we now write the equations here, body is moving in a circular path. So, therefore, what we have is in the vertical direction, if we call this as the z direction, if we call it as the r direction. Now, in the z direction we have T cos theta is the force by tension minus mg, these are the forces, and the body is not moving in the z direction at all. So, acceleration in the z direction is 0. So, the z direction Newton's law gives us T cos theta minus mg is equal to 0. And in the radial direction we have only a single force which is equal to T sin theta, and this must be equal to mass times acceleration in the radial direction. So, this is equal to m times v square upon r. So, we have these equations, and from here what we get is, if we look at first equation, so T cos theta minus mg is equal to 0 and T sin theta is equal to m times v square upon r. And also we have shown, if L and theta are our two variables, then r is equal to L sin theta. So, from here when we work this out, what we get is the velocity T tension is equal to mg divided by cos theta, and v square is equal to root of v is equal to root of gr times tangent of theta. So, this is how we get, if the ball has to move with a speed v, then the angle theta which it will maintain will be given by this, and r is L sin theta. So, we can convert things in terms of the variables we have. So, we would like to work out the time period of the pendulum. Time period of the pendulum will be equal to the circular distance moved by the pendulum divided by the magnitude of the velocity or the speed. So, therefore, this will be equal to 2 pi r divided by v, and when we work this out, this will be equal to 2 pi r divided by v. V was root of gr times tangent theta, and when we put r is equal to L sin theta, then what we get is that the time period will be equal to 2 pi times root of L cos theta upon g. And this gives us an interesting fact, that the time period of this conical pendulum is only a function of L cos theta, and L cos theta, as we have seen, if this is the conical pendulum, this is the angle L, this is the angle theta, this is L. L cos theta is nothing but the height of the pendulum. So, if we have 4 or 5 conical pendulums rotating about the same base, and if they have different lengths, then if the time periods is same, then they will be all in the same horizontal plane, because L cos theta will be the same. So, that means the angles theta will vary, but they will all move in the same horizontal plane. So, this is the conical pendulum. Now, let us try to analyze about bodies moving on a circular track, and we will assume that the body is moving with a constant speed. So, as a, let us say we have a car which is moving on a highway. It is first moving along a straight section, and then it comes across a turn. So, at a turn, it goes in a turn, it is a circular arc, and when the body is moving in a circular arc, then as we have seen, there has to be a radial component of acceleration which is there. Now, if the body is moving, let us say this is the straight part of the track, is moving along a straight part of the track with a constant speed. So, then the acceleration on the body will be 0, and no force will be required in that particular direction for the body to move. But once, so therefore, let us say this is the body which we have, this was moving. So, take this as the body, it was moving along a straight path, assuming if it is just moving along the straight path, but once it comes on a curved path, then there has to be some external force which has to provide this radial component of the acceleration as it moves along the curved path. And this radial component of the acceleration is what is provided by the friction. And in this case, we will assume that the friction force which is in the direction of the motion of the car, that is in the tangential direction, let us neglect that. But just to provide this radial component of acceleration, a friction force has to be there in the radial direction also. And let us try to draw the, if this is the body moving on a circular track. So, let me now show this as a, in the figure on a plane. So, we have a curved track on which a body is moving. Let us say the vertical direction is Z, this is R, and so now what I draw is, I draw the free body diagram of the particle, and I look at the RZ plane. So, in the Z plane what we will have is, we will have the normal reaction and we have the weight. So, this is in a, so this Z plane is perpendicular to the paper. So, here Z is coming out of the paper, and I am looking at the free body diagram, and when I draw the free body diagram, this is the Z direction, which means this is the direction. So, I am looking at a view of this paper perpendicular to the paper, and towards the center in the R direction, if this is the R direction, what I will have is that there has to be a friction force which is acting on the wheels, and when I now write my equations, what I will get is N is equal to mg, because there is no acceleration in the Z direction, and the friction force has to be equal to mv square upon R. This is in the R direction. So, therefore, what we get is the friction force between the road and the particle in the R direction. This is what provides centripetal acceleration. But we realize there is a limitation with the friction force. What we know is friction force has a limiting value and maximum value of the friction force is equal to mu s times n, and once the body starts to move, then friction force is equal to mu k times n in the direction opposing the motion. So, as long as we have friction is equal to mv square by r. Now, and we also know n is equal to mg. So, maximum value of friction force will be equal to mu s times n, which will be equal to mu s times mg. Now, if the particle moves along the circle with a large V or less r, that means it travels the curve with a lower value of radius or with a large value of velocity, then it is possible that the friction force or F max is less than mv square by r. Now, if the maximum value or limiting value of friction is less than mv square by r, then what will happen is once this value is attained, the motion, uniform circular motion will not be possible. Why will it not be possible? Because friction can have a maximum value of mu s times mg, but this the V is so high that it has exceeded the value of mu s mg. Mv square by r is greater than mu s mg. So, for this mv square upon r has to be greater than mu s times mg, and if that happens, then the body will start to move out, because once this happens, so this circular motion will not be possible, and what will happen is we will have the body starts to move such that r becomes large, because that is the only force which friction can provide, and so because that is not there, so the acceleration is there in the opposite direction, friction is not enough. So, we have an acceleration in the opposite direction to slow this motion. So, therefore, r becomes large, and this is what we term as skidding of the car. So, the car starts to skid in a outward direction on the circle. So, to prevent skidding, therefore, what can be done? Well, normally what we will realize is skidding will happen, it is possible when on a surface where mu is low. So, that is why when we have icy surfaces, then there is a possibility of vehicles skidding when they go along a curve, and therefore, to prevent skidding, what should the driver do? They should reduce V or increase R. Now, if the road has a fixed curve, then R cannot be changed, then the only way to prevent skidding will be to reduce V, and it is very effective because it goes like V square upon R. So, when you drive and to reduce skidding, this can be done. Now, there is another thing which is done on highways to reduce skidding, and this is what we do is the highway is tilted at an angle. If we have a curve on the highway, so what we do is it is tilted at an angle, and this is what we call as banking of the road. So, the vehicle as it goes, it's this road is tilted at an angle theta and it is higher on the outside and lower on the inside. So, there is a slight angle is given to the road which is termed as banking. And what is the advantage of banking? What will happen now is the normal reaction is not vertical, it is at an angle. So, normal reaction now is at an angle, and what if we look at this, if we draw the free body diagram, this is mg, this is n. So, now what we have is mg is equal to n cos theta, and a component of normal reaction n sin theta, which is the component of normal reaction, this is the one which can provide the force, the centripetal acceleration. So, a component of n this provides the acceleration in the r direction, and assuming we have a case where friction force is 0, there is no friction, then what we have is n sin theta is equal to mv square upon r, and n cos theta is equal to mg. So, from here we can work out, and what we have is for a road which is perfectly banked, that means we do not require any friction, we can work out the angle of banking theta for a well designed road. And what we get is the same thing, n is equal to mg upon cos theta. So, mg tan theta is equal to mv square upon r, and we get the same thing, v square is equal to rg tan theta as we got in the case of a pendulum. So, therefore, we can work out the angle of banking, that tan theta is equal to v square upon rg gives that angle of bank, so that if the car goes with this speed and the radius r, that will be designed so that there will be no skidding, and the normal reaction itself will provide the force for the centripetal acceleration. Now, so we have seen some of these problems of circular motion. Let us look at briefly look at a topic of what happens when we have friction force on a body which is in contact with a fluid, and by fluid we mean it could be a liquid or a gas, and the examples of this would be aeroplane traveling in air, or we could have a block this is a block moving on a table, but instead of there is a layer of, let us say, oil between the block and the table. So, in effect what we are trying to see is what is the effect of this contact force of the liquid or of the gas on the body. What we have seen is when the contact is between two solids. So, let us first look at the case of Coulombic law of friction. When the contact between two solids, so there is body 1 in touch with body 2, then what we say is at the point of contact we have, so let us say I am drawing the free body diagram of body 1. On point of contact what I show is there is a force in the normal direction which I call as n, and a force in the tangential direction which I refer to as the force of friction. This is what I do when I have contact between two solid bodies. And what our modeling tells us is that this friction force is less than or equal to mu times n. When the bodies do not move, there is no relative motion, then this friction force is less than mu times n, but when there is relative motion, friction force is equal to mu times n. So, that means the friction force is written as a product or as a directly related to some other force, and that is what happens when the contact is there between two solids. But when we have a solid in contact with a fluid, so we have, let us say, this plane and which is moving with the velocity v, let us say the acceleration is 0, and surrounding this is air. So, now the air will also exert some force on this body, and the friction. So, the force in the tangential direction which we will say, so here now what we will have is, let us say on this a force F is being applied on this body, and so that it is moving at a constant speed F, the friction force due to air on this body, and this friction force is a force which is opposing the velocity v. We call this as a force equal to, we represent it as a single force, we call it as the drag force. And the drag force, we find drag force d is a function of the velocity v. The body is moving at a velocity v, so the drag force is a function of v, and this is the difference between solid friction and fluid friction. In solid friction, when the contact was solid, the friction force was proportional to the normal reaction which was a force, and in case of a fluid friction, the drag or the friction force which we have, this is a function of velocity and not a function of force. And what we find is that if this drag force which we write, if the body moves at very slow speeds, then the drag force is proportional to v, and if the body moves at high speeds, then the drag force is proportional to v square. Well, it could be in general a function of v, but this is how what we take it, and for high speeds, for bodies moving at high speeds, the drag force sometimes is represented as half times c times rho of the fluid times v square times the area. So, we have a body which is moving like this with a velocity v, the drag force on this, which is the force in the direction opposite to the velocity because of this surrounding fluid, this will be half times c. This c is a constant which is dependent on the shape of the body. Rho of the fluid is density of the surrounding fluid, and in general this A is the frontal area of the body, which means if we project the body on a plane, the area will be given by A. So, for example, if this is a sphere, so if the body is a sphere, then the area A will be equal to pi r square, where r is the radius of the sphere. So, now let us take the case of a body which is falling in a fluid. So, suppose we have a tube filled with fluid and this is falling in the fluid. So, here what we have is, in this case if we say the drag force is equal to half into CD into rho f into V square times A. Now, what is, if I draw the free body diagram of the falling body, then what I have is its weight is acting down and in this direction we have the drag force which is acting upwards. Now, what will happen is, as the body starts to fall, initially it is at a 0 velocity, so there is no drag. So, because of the weight the body starts to accelerate. So, therefore, what we will have is that mg minus d will be equal to mass times acceleration of the body. But slowly the velocity increases, and as the velocity increases the drag force will increase. So, as the drag force increases, then what will happen is this acceleration will come down and eventually the acceleration will become equal to 0. And this is what we call as the case of terminal velocity. When the body starts to move with 0 acceleration, we call it as terminal velocity. And when we, in this case, when the body has achieved terminal velocity, then acceleration is equal to 0, and what we will have is mg is equal to d, and if we write the drag force as half c into rho v square times a. So, from here what we get is the terminal velocity square is equal to 2 mg divided by c times this rho is rho of the fluid times the frontal area of the body. So, this is how one can get the expression for the terminal velocity. But if Vt has not been achieved, then we still have mg minus c times half rho f v square times a is equal to mass times acceleration, which is equal to m times dv by dt. And so, now if you have to find the expression of velocity as a function of time, you have to take whole of this left hand side as a denominator, take the dt on the other side and then integrate. So, this of course all of you may not realize, but this is how we do it. But once, if you have to find the expression for the terminal velocity, then we can get it like this. And now let us look at an example of a raindrop of radius r is equal to 1.5 millimeter, which is falling from a cloud of height h is equal to, let us say, 1500 meters. It is given to us that c is equal to 0.6, density of water is equal to 1000 kilogram per meter cube, and the density of air is given as 1.2 kilogram per meter cube. And we have to find the terminal velocity of the raindrop. So, if we draw the free body diagram of the raindrop, we have this mg, we have this drag force, and because we are talking of terminal velocity, these two must be equal. So, mg is equal to d, which is equal to half c times rho f times Vt square times a. So, now for this particular thing, let us work it out. The m is equal to rho of water, that is the density of water times the volume of the drop. Volume of the drop will be 4 by 3 pi r cube. M times G is equal to half C is given to us, rho F is given to us, and we look at the area A. Area will be equal to pi r square. So, when we put both of these in this expression for mg is equal to this, what we will get is Vt is equal to square root of 8 r rho Wg divided by 3 times C times rho A, and putting in these numbers what we will get is this velocity will be equal to 7.4 meters per second. We will put everything in SI unit, that means we will have to convert 1.5 millimeters to meters. Now, we realize this answer is independent of H, and had the raindrop so we have this as this way, had D been equal to 0, then falling height of 1500 meters, velocity would have been equal to root of 2 times G times 1500, which would have been of the order of something like 200 meters per second. So, it would have been a very large velocity, whereas because of the effect of the drag force it becomes 7.4 meters per second. And this tells us that, and also what we realize is the terminal velocity is independent of the height of the cloud. So, therefore, whatever be the height of the cloud, once the raindrop reaches 7.4 meters per second for these given conditions, it will just continue to fall at the same velocity. And that tells us why we are safe, otherwise possibly all these raindrops which come from very high heights will cause a lot of damage on the surfaces. Now, also related to this concept of the terminal velocity is this very famous experiment by Galileo from the Leaning Tower of Pisa. When Galileo talked of free fall, and we probably discussed this when we talked about kinematics, then what he said was that if you take a stone or if you take a feather or a light ball, any body, and if you take them to any height, and then they should reach ground at the same time. If we drop them from a particular height, they should reach ground at the same time. And we realize that a stone, when we actually do if we go to the Leaning Tower of Pisa and from the top we take a stone and we take a feather or we take a ping pong ball of the same volumes, and if we drop them we will find the stone drops much faster as compared to the feather. And the reasons for this now become obvious. It is because of the drag force, and as we have seen, the terminal velocity goes like so. If the bodies have the same geometry, then rho f, a, c and 2 and g will be the same. It will depend on the mass of the body, and the terminal velocity will be achieved much higher for a body of a larger mass. So, therefore, if you take a ball of lead and a ball of wood, the ball of lead will reach the ground earlier, and that is because of the effect of the drag force. And actually now, if you go to a lot of these science museums, we have these experiments being done there, where in vacuum you have a feather and a ball being dropped from the same height, and because in the vacuum the raw fluid, the terminal velocity is not there, there is no drag force, because there is since you have created a vacuum, so there is the fluid does not exert any friction on that. You do find that whether you drop a stone or a feather from the same height, they reach the ground at the same time. So this is how the fluid friction, therefore we have seen how this is to be accounted for in simple problems. Well, of course, it turns out when we will study later on the concept of viscosity, then this drag coefficient would be related C, this is what we call as the drag coefficient, and this is related to the fluid viscosity, and the symbol typically used is eta. So, this we will talk of in a later time when we talk about this. So, what we have seen is we have looked at these problems where we have solved problems involving forces on bodies, and what we have seen is that we are basically, to solve these problems of mechanics, we are using the equation F is equal to ma. This is the vector equation. We divide it into its scalar components, and we will say Fx is equal to mass times acceleration in the x direction, Fy is equal to mass times acceleration in the y direction, or Fr is equal to mass times acceleration in the radial direction. And in the problems which we saw, in one of the components, but the y or the z component, the acceleration was 0. So, the force is balanced out, and in the other direction we worked out F is equal to, we applied this equation F is equal to m times a and solved the problems. The problems we have solved are reasonably simple in nature. In another problem solving session which I will call, I will take up some more complex problems where there are more bodies which are connected to each other, there is a constraint of motion. So, those type of problems we will do in that session. But in terms of topics, the next topic which we will do is, here we have seen applying Newton's law in the form F is equal to ma. Now, what we can do is, acceleration can be written as dv by dt. So, this we can either we can take this dt on the other side, we get F dt is equal to m times dv. This will give us, as you will see, the concept of impulse of a force. Also, the other thing is, we have this acceleration, we have seen, we can write it as is dv by dt, and this we can write as dv by ds into ds by dt, which is v times dv, and when we put it in this form, this is where, using this form, we will get to what is called the work energy formulation. So, after the problem solving of involving this type of techniques where we use acceleration directly, we will introduce this concept of what we call as the work done and the integral of v dv, which will lead us to the concept of kinetic energy, and we will look at work energy formulation and impulse momentum formulation of Newton's law.